the most important problem in chemistry, that is hydrogen atom problem. But before we start doing, I I must spend some time on particular box. Uh, uh, so can you see the file which I have here? Can you see the plots?
Yes, sir.
Yeah. So this is a plot of your psi2, n equals to 2, the second level of particular box problem, and square of that, essentially the probability density for n equal to 2 state of particular box. We have one node, you can see there. Remember what is psi2? Psi2 had one node. So if this is psi2 square, is it okay? This is how the probability looks like. Is it fine? Please write in the chat box. This is for a particle in a box.
Yes,
Just
sir.
revisiting the problem. If I go to higher, for example, n equal to 3, it will be something like this, isn't it? Shown here. And if I go even farther, higher, what do I expect? So if I go higher, for example, if I take n equal to say 10, then my profile would be something like this. How many nodes will be there? There will be 9 nodes, and it will oscillatory like this. Okay. But if I go to very, very high quantum number, what do I expect? Actually, high quantum number means high in energy. And if I take a classical particle inside a box of length L, the classical particle cannot go outside. Even a quantum particle cannot go if the potential is infinite. Then what is the probability of finding that classical particle inside the box? It is something like something constant, isn't it? It's constant. So when you go to very high quantum number, you will see the probability density. If I plot for very high quantum number, say in 100 or maybe even higher, it will look something like this. And you can see that a lot of oscillations, many nodes, and the nodes are very close to each other. And you see that what happens at higher quantum number, your probability density is kind of constant. So for example, I can plot this along with other quantum numbers. For example, if I plot this with quantum number 1 and 2, you can see the blue one is 1 hidden, and the red one is for 2. Okay, I can change the color if you want. That's good. Maybe if I change the color, maybe you can see. So you can see maybe this the red one is for n equal to 2, the dark blue one is for n equal to 1, and the cyan one is for very high n. And you can see that when I go to high quantum numbers, my probability density becomes more or less constant. So as if we are approaching a classical world. So this is what happens when you take a quantum problem and go to higher quantum number. So higher the quantum number, you're more close to the classical world. Okay, this is something loosely I can call it quantum classical correspondence. Okay, so I think many of you knew about it, I'm sure. And one more problem I think we should mention very briefly if possible, and that problem is called particle in 3D box. And this is quite important because when you do particle in 3D box, you can relate to this problem too loosely to a problem, say inside a metal, say electron in a metal. So I'm not going to do this problem in detail because I have done particle box in 1D box in detail. So let me draw 3 axes. This is hand drawn, so it is not going to be a very good one. So this is your X, this is your Y, this is your Z. And then I have a box Along x-axis, the length of the box is L1. Along y-axis, the length of the box is L2. Along z is L3, and then I can draw a box like this. No? So this is a box uh, which I have in 3 dimension. Okay, so I should have drawn like this. Not very well drawn. Okay, and when I do this thing, so sorry. If I sorry for this, something like this. Okay, so this is your L1, this is your L2, this is your L3, and the potential is such that V of x comma y comma z is infinity outside the box. This is 0 inside. We'll make our problem slightly easy by assuming, okay, my potential is written as a sum of 3 potential. Your V of x comma y comma z, I write it as uh, sum of 3 potential, like uh, V of x plus V of y plus V of z. This potential is chosen in such a way that, okay, the condition I had written already, that is satisfied. Okay, what is the condition? So if I take V of x, it is actually 0 when you are within this. This is infinity otherwise. Similarly, V of y is 0 when you are within this length. This is infinity otherwise, and V of z is 0 or infinity when you are otherwise. The good thing about it is that if any of these conditions is not satisfied, that your particle is not between 0 to L1 in along x or 0 to L2 along y, any of this, your potential becomes 0 because one of the terms will become potential will become infinity because one of the terms will become infinity. Okay, so if I can write my potential in such a way that it's a sum of potentials in 3 directions, so this is the way I write, and then I go back and write down my Schrodinger equation, which is my eigenvalue equation, which I want to solve for this problem. What is the eigenvalue equation? I have a eigenvalue equation like h cross square by twice m. This is in 3 dimension. So I'll have my kinetic energy operator will have this one, and then I have the whole thing will be plus a potential which is given by this, which is Vx plus Vy plus Vz or Vz. The whole thing operates on some wave function which is a function of x, y, z, and that gives me something like energy which is equal to psi of x comma y comma. Okay, I am hoping that you are following. Okay. So the next thing is that what I'm going to do, I'm going to use an approximation, the similar approximation I use, because what I'm solving a boundary value problem. And we adopt a technique called separation of variables. I think I can make it slightly bigger. Okay, so this is what I'm going to do. So the idea is that since my potential energy is written as a sum of potential energy along three different axes, I can have a choice that my total, the wave function, which is a function of x, y, z, can be written as a product of three functions. This capital X is not small, it's capital X, which is a function of x times capital Y of y, then capital Z of Z. So product. Okay. So this capital X is a function of x only. This x only. Similarly, this is function of y only, and this is function of c only. And if I adopt this scheme, then my life becomes quite easy, because if I take this and put back in my Schrodinger equation, you will see that my Schrodinger equation I can rearrange and write it like this. I hope everyone is following. If anyone has a problem, please ask. This is very simple, because if you have followed my previous classes, you should be able to follow this. Okay. So this is something like E, and then on your left, you're going to write functions like this. Okay. So what should be there? It should be the total function here, no? The same thing should be here. You should have xx, yy, z. Similarly here, same thing. Similarly here, same thing. I'm not writing, okay? This is the structure of your Schrodinger equation, the time independent Schrodinger equation. Okay? Anyone has a problem, please write in the chat box. Fine? Is this fine? I hope this is fine. Okay. So now the next thing is what I did in case of separating the time independent Schrodinger equation to time independent one. So I just divide the whole thing, divide the thing with the total wave function, so psi of x comma y. So divide both sides by this. Okay. Now before I divide, just look at it. This operator, this depends only on x. And so it will operate only on this function. This will not operate on this. So these two, I can take and put it here. Is this fine? Please write in the chat box. Yeah. Okay. Similarly, here this operator depends only on y. This operator depends only on z or z. So similar things I can do in this case, the x and z functions, I can put it here. In this case, x and y functions, I can put it here. And then when I am dividing both sides by the product of three functions, the first term will give me something like 1 over, maybe you can tell me, you'll get me 1 over
X of X.
yes. But the whole thing is operating on
X of X.
Then I have similar term in y, not writing, similar term in z, and on your right you have e. Constant, it's a constant. So again, look at carefully what is here. You have here something which depends only on x. You'll have similar, depends only on y. And here you'll have something only on z. So how it is possible? When it is possible, tell me. This is possible only when, if you add these three and then you get something constant, it's possible only when all of them are individually a constant, isn't it? So what I'm going to
Yes, sir.
do, I'm going to write like this. So what I'm going to I have it, that first equation I'm going to write like this. This is first equation. Let me write it down. So I will write, this is h cross s square by twice m. I'm writing h cross s square by twice m. Okay, and I'm not going to write partial derivative anymore because it's not necessary. Okay, the whole thing operates on x of x, and what I get on the right hand side, because essentially what I've done, I've multiplied with x of x, so I'm going to get a constant which I'm calling e1. I hope you are following.
Yes, sir.
This is very simple.
Yes,
And
sir.
similarly, I'll get another equation for some problem with this. Okay, and so on. So for z direction, I'll get something like, okay. Now you know all these individual equations. You know them quite well, isn't it? Because these are like particle in one-dimensional box, each of these equation, and you can solve it. And when you solve it, you get equation like this. So essentially, what you see, that if you solve, the total energy would be something like E1 plus E2 plus E3. And I can write it down. I'll have three quantum numbers, each along one axis. So I'll have something like n1 square h cross s square. What was that? 2m l1 square. And that was the expression. If you check your particle in a box, then I'll have n2 square h cross s square twice m square plus Please tell me that this is correct.
Sir, n square, h square, pi square. Sir, pi square term will also be there.
I think this is correct. This is not correct. Some pi is missing, I think.
Okay. Yes.
This pi square is missing, no?
Yes.
Okay. Yeah, sometimes I'll deliberately or sometimes I do some mistake. So this is the energy. So when your E1 is this, E2 is this, E3 is this. You knew it, I think, all this, because if you know 1D box, then you know 3D box. So your E1 is this guy. This. This. Now consider a special case. Consider a special case where your L1 equals to L2 equals to L3. I'm calling it L. This is called cubic box, isn't it? In that case, what will be the energy expression? Your energy expression is going to be something like equals to, you see this N1 square, H plus L square, pi square into twice M L1 square. Now L1 has become now L. It should be L. L square plus N2 square, H plus L square, pi square by L square plus N3 square, H plus L square, pi square by M L square. And then I can do one thing, because it's a cubic box. I can take the whole thing common. I can call it, say, chi, something like chi into. This is fine. Where chi is not a function, it's a number. Chi is this constant. This is something like h plus s square, pi square by m l square. So what is the lowest possible energy in this case? Okay, before I do the energy, I can do one thing here. So if you have, this is the expression for your energy, then just solving particular box, I can say my wave function, which is going to be a function of x, y, z. I told you, and also it's a function of n1, n2, n3, a function of x, y, and z. It depends on three quantum numbers. It is, in general, it is going to be 2 by L1 sine n1 pi x by L1 into 2 by L2 sine n2 pi y by L2 into 2 by L3 sine n3 pi z by L3. Is it fine?
ল্যাপটপ বোর্ড না, এটা বোর্ডের মতন কিন্তু ল্যাপটপের উপর।
Excuse me, someone's microphone is on and he's talking. Okay, so this is my wave function. Okay, anyway, I'm coming back to the energy because I want to finish this as soon as possible and I want to move to the real problem, Harian problem. So your expression is like given by this, and you know the lowest possible values for these quantum numbers are 1. So if I choose this, again something happened. Okay. Oh, there's no problem. So this is the lowest possible value. Then this energy is, can you tell me what is the answer? This is going to be 3 chi, isn't it? This is E000. I can call it E000. What will be the next possible energy? I can have 100, not E00. You should tell me. This is E111. Are you guys there or sleeping? Are you guys there?
Yes, sir.
Okay,
Yes,
yeah,
sir.
yeah.
Yes, sir.
Yeah, don't sleep, huh? So next one I'm calling 211. What will be the answer?
6x.
It will be 4 plus 1 plus 1, 6 chi. Something happened to my pen. But it is also possible that I have a situation like 1 to 1. What is the answer?
6x.
Second.
Same.
6x.
This is again 6 chi. This is chi. And then I can have a situation like E 1, 1, 2. This is again going to be
6x.
not chi, not a.
Sorry. Sky, yeah.
Because of my handwriting, I have some problem with this pen now today. Okay, so but again I go to this E22. 2. What is the answer? The answer is 2 plus 2 plus 2, 2 square plus 2 square plus. What is that answer?
9.
2 to 2 is 9.
No, sir.
12.
12. Is it anything? Is there anything between this?
311.
2, 1, 2.
111 is done, no? Now if I have 211, what is the answer? 211 answer is
6 chi. 6 chi.
It is 4 plus 1 plus 1. This I have done, no? Then what? 2 to 1. What is the 2 to 1? Not 2 to 1, 1, but 2 to 1. What is the answer?
6 chi.
9.
9.
9 chi.
Yeah, and then you'll have other things for this, no? Same value, but different quantum numbers. 2, 1, 2. Also something like 1, 2, 2, and both are having the same energy. So all this 3, and they are degenerate. So in energy. Sorry, convince that they're degenerate in energy.
Yes, sir.
Yeah, yes, sir. Degenerate. Some problem with my. I don't know what is happening. Idea. I go to the next slide maybe. So there. Yeah. So basically what I have, let me write down. So if I put an axis like here, E, okay, the lowest possible value is what? We have just, yeah,
3 chi.
3 chi, say maybe this is your 3 chi, which is the case for your 111. What is the next one?
1,
Next one was actually, you had like 6 chi, but there are 3. So that level is degenerate. So we'll have here, and I'll have 3 very close this energy level. This is energy is 6 chi, and this is for 112, isn't it? 121 and 211. What is the next one? Next one is 9 chi, I think, isn't it?
Yes, sir.
I have to check.
Yes, sir.
I think 9 chi, yeah. So 9 chi will be something like here, and this one is for, this is for 221 or 212 or 122, isn't it? And after that I have another one, which is
311.
right. 311 is there also, yeah. Yes, you're right. So this one is 222, but you say that something in between, you can have a 311, which will be energy like this 9 plus 1 plus 1, which is 11 chi. But then you'll also have 1 1 3 1 3 1. Okay, so you'll have something like here 3. Okay, so what I can see, that what I'm saying, degeneracy, by degeneracy I mean that their energies are same. If you see, these are degenerate levels. Okay, and this is not present in 1D, but if you go to 3D as well as in 2D also, if you do 2D box, you will say these are called degenerate states. I think I'll conclude here because I don't want to carry this further, and you can just check in the internet how to plot these wave functions. This is not easy because the wave function itself is 3 dimension. How to plot? Functions for that you can check in the internet. Also, you can see the Professor Sebastian's lecture. I think it's nice. So idea is simple because, for example, if I go to psi 111 and this is actually given by 8 by L cube sine pi x by L sine pi y by L and sine pi z by L. No node. This is fine, no? No node for the lowest possible energy level. And if you try to plot this in this 3D, and this is your box, whatever. It's not very well drawn because it should look like a cubic box. And if you plot, it is obvious that at the boundaries these wave functions vanish, but then it is a sine function. So it is something like in 1D, you know, in along x direction, it is something like this. If it is x, okay. So people plot it like this. They plot using shades. So I can use shades like this. So you have a face which is very, very dense, and as you go towards the boundary, the shading becomes lighter. And you can go to the internet and check. Okay, this looks like something like an x orbital, isn't it? You remember orbital?
Yes, sir.
We'll go to the orbital. But I can go to the next energy level and next wave function, say psi 1. I make it say 1 1. No, I make it 2 1 1. Now 2 1 1. If you plot it, you can guess what is going to happen. I draw another box here. Very badly drawn box, but they'll have one node here, and this 2 1 1 will have a node along x. So you'll have, if you plot, you will see that it will look something like, if I just look something like this. This is your x axis, and this will look something like your p orbital. This is something like, looks like S. This one looks like p orbital. So with that, we'll stop discussing particle in a box related problems, and we move to the most important problem in chemistry, I would call it, and this is called hydrogen atom problem. How many of you solved this hydrogen atom problem? And this is a kind of problem. This is a real system because hydrogen atom exists, real system, and can create hydrogen atom in isolation. And the most important thing is, this is one electron system, and good thing is that it's exactly solvable. Okay, so please tell me how many of you have done this solution, or how many of you know at least qualitatively this one. I hope everyone. Can you write down in the chat box how many of
Yes,
you?
sir.
Yeah, I think many of you know. I hope many of you have done it. Okay, so let me start by writing the Hamiltonian. If I write down the Hamiltonian of the system, because you know this hydrogen atom problem, you have a nucleus and you have one electron. That is the problem. So for the nucleus, I have a kinetic energy which I call it h cross square by twice m, where m is mass of the nucleus. So essentially, in hydrogen atom, you have only proton there sitting there. Now h cross square by twice m, but then I'll have a grad square r. This is fine. This is fine. Not r. Sorry, I should not use r. I am going to use for something else. Grad square n. N for the nucleus. So if I write like this, it's fine for to everyone. Should be fine, I think, because this is so this is a derivative derivative involving nuclear coordinates, isn't it? Then I'll have another term, which is the term that is your kinetic energy of the electron. What is that? This is fine if I write down this.
Yes, sir.
Yeah. So this is derivative involving electron, coordinate of the electron. The electronic coordinates of the coordinate of what else? Because you know the nucleus has proton, because of that is positively charged, and the electron is negatively charged, that you know, and they interact through Coulomb interaction. You know that? Okay. So then I should have E square, E times E, with a minus sign because it's attraction. In SI unit, I will have 4 pi epsilon 0. And then I'll put something like, which I'm going to define now. So this is the distance between electron and the nucleus. That is what I have put there. Is this fine so far? This is the Hamiltonian of the problem. Okay. Okay, this problem, you want to solve this problem, huh? Now the problem is what? The problem is this H operating on some psi gives you something like E times psi. That is what you want to solve. Okay. Is this fine so far? So let me draw it here. Maybe I'll draw it here. So if I say okay, I have to choose a coordinate system like the one I have chosen here, and I put this guy here. This is my nucleus. If this is a nucleus, then if I join this nucleus to the origin of that coordinate system, this will give me, this is given by a vector, and this will give me the position of the nucleus. Okay, and then I can draw an electron here. This is your nucleus, this is your electron, and then I can also join this electron to the origin, and this will give me something like the electronic coordinate. and the distance between these two is given by this. These are all vectors. And Re minus Rn, if I take a mode of that absolute value, this gives you the distance between electron and the nucleus. Fine? Up to this should be fine. Any question so far? So let me write down the Schrodinger equation which I want to solve. This is the Hamiltonian. I'm not writing it again. H operating on psi. Now this wave function should depend on what? In principle, it should depend on electronic coordinates and nuclear coordinates. And that should give me something like energy of the system and then the wave function back. Is that fine? Any question so far? Tell me if you have a question, please ask me. I think this is quite straightforward. Now look at carefully. This psi I have written here. This is a function of how many variables? Of how many variables? 6 variables. Yes. Well, how? So let me draw it again in the next slide. Let me write again because your wave function now depends on your nuclear as well as electronic nuclear coordinates, and R will have something like XE, YE, ZE, and this Rn will have Xn, Yn. Yeah. So the Schrodinger equation which I have written here, is this one. And this is not easy because this is a function with 6 variables, and this Hamiltonian also involves 6 variables. So this is something this is involving partial derivative with respect to 6 variables. No, this Hamiltonian that involves partial derivative with respect to 6 variables. Hamiltonian shown here. It involves partial derivatives. Involving 6 variables. Okay. So we have partial derivatives involving 6 variables. Okay. And actually, in classical mechanics, people who have studied classical mechanics, they would know this is something like a 2-body problem, but there's a way to solve this 2-body problem. And what I'm going to do today is as follows. We'll see that we'll split this problem into 2. One is center of mass problem, and other one is and for the relative coordinate. So let me take this. What I do, I take this. I just take this R of n, multiply this, the mass of the nucleus, plus R of E multiplied with the mass of the electron, and divided by the total mass. This is a vector, the whole thing. I'm calling it capital R. And you have a name for this vector. How many of you know this? There's a name to this. What is this? Yes, I have already written there. Okay, this is vector center of mass. Similarly, which I have already done, I have another vector which I am calling it small r. This is nothing but your Re minus Rn. And this is called the relative coordinate. And now I want to write the whole thing in terms of these two. Okay, is this fine? So what I'm going to do, I'm going to change this to relative coordinate, this change of coordinates. So now if I write down the Hamiltonian, you remember what is the Hamiltonian? Hamiltonian was something like x and sorry. That was Hamiltonian, no? Which we had started with. Okay, and then you have this. Let me write down it explicitly. And the whole thing is operating on whatever leads to this. There is a problem I want to solve, but now I have made a change in variables. So change of variables. If I do the change of variable, this thing is going to change. Now first we'll not do the math. Even without doing the mathematics, we'll try to guess the physics. Okay, if I go from this electronic coordinate, nuclear coordinate to this center of mass and the relative coordinates, then what should be the Schrodinger equation, of course. So let me write down the first term. First term is going to be, when I talk about the center of mass motion, what should be the mass for this center of mass motion? What does it mean physically, center of mass? Just I hope you can see me. So this is your electron. I don't know how to show the electron. Okay, maybe this is your electron and this is your nucleus, isn't it? Nucleus is here, electron is here. Electron is revolving around nucleus if you follow the classical Bohr's picture. But that is your two body problem. Essentially, you have a nucleus, you have an electron. And center of mass motion means the whole body, so including the whole system. The nucleus as well as the electron, the whole system itself is moving. Okay, so the movement of the whole system, essentially the movement of the hydrogen atom all together along with the nucleus and the electron. So that is called center of mass motion. So for that, what should be the mass? Can anyone write down in the chat box? Yes. What should be the mass for such motion, center of mass motion? Okay, reduced mass is not the correct answer. The correct answer is your total mass, because center of mass is the motion of the whole system. Whenever I say center of mass motion, means center of mass is the motion of the whole system. Why? So let me draw this. If I draw a very crude picture, you have a nucleus here and you have electron here, where since the nucleus is much heavier than the electron, I would expect the center of mass somewhere here. Somewhere here, for example. And this is your whole system, no? So when I talk about the whole system moving, if the whole system moves, then what will the picture? The picture will be something like this. The whole system moves. Maybe some later time, your nucleus is here, electron is here, and your center of mass is here. So essentially what I'm following the motion of the center of mass. This center of mass has moved to here. Okay, because we are not interested in right now the what I'm talking about. Not interested in the motion of electron with respect to the nucleus. Right now we are looking at the motion of the whole body. Center of mass is here. It's like a translational motion. So center of mass motion is like the translational motion of the whole body. Okay. Whole system. Okay, so this is important that so we're looking at the translational motion of the whole system when we talk about center of mass motion. So in case of center of mass, your mass should be 2 times the total mass of the system, mass of the nucleus plus mass of the electron, because the system is composed of the nucleus and the electron. Okay, and then I'll have a grad square. Now I'll not use grad square R, grad square N. I'll use the center of mass. Okay, this is fine. What will be? So I'm writing down the Hamiltonian only. Okay, first write down. What is the next term? Next term is going to be h cross h square. Now by 2, and then I have to put a mass here. And now I am talking about this relative coordinate. Relative coordinate is this, given by this. It is Re minus Rn, the separation between electronic and the nuclear coordinates. So the relative coordinate motion means what? Basically, I'll just look at the motion of the electron with respect to the nucleus. Okay. So if I go to very old, your Bohr's picture, many of you, I think hope you remember Bohr's picture. Do you remember Bohr's atom picture? We did not discuss, but I think everybody knows. Please write down in the chat box that you remember Bohr's atom. Yes. So if you go to the Bohr's atom picture, you will see that, okay, I have a nucleus sitting there and I have a circular orbit and my electron is here. When my electron is here, where is your center of mass? Center of mass is here. Okay. And when the electron is here, if the electron revolves and comes here, well, your center of mass is going to be where? If the electron is here, if the electron revolves and comes here, then your center of mass is going to be changed, isn't it? Okay. Your center of mass is going to be here. For the system, I'm talking about the different snapshot. I'm not looking at the whole motion of the system, but within the system, if the nucleus is here, if electron is here, the center of mass is here. But when the electron is on the other side, the center of mass would be here. So center of mass is going to change. So your mass cannot be center of mass in this case when you talk about relative coordinate. Are you okay with it? That center of mass, you cannot put it there because you are not looking at center of mass motion. You are looking at relative coordinate. Can we put electron mass there? In that case, can we put an electron mass there? Mass of the electron. Tell me. Write down in the chat box. Write down in the chat box whether we can put the electron mass. Somebody says no. Why? Because when I talk about the relative coordinate, yes, I am talking about mostly electron, motion of the electron. The nucleus is also moving slightly, isn't it? Because it is not only the motion of the electron, it is also the motion of the nucleus. Though the nucleus is much heavier, it is moving much slowly, but it is also moving a little bit. So I cannot put, we are not looking at exactly the motion of the electron only. It is the motion of the relative coordinate. So you will see that you will come eventually see that some effective mass will come here. This is called mu. And there's a name to this. How many of you know the name of this effective mass? How many of you know this? Can you write down what is called, what is this mu? This is called reduced mass. Okay. And so you'll have a now grad, but involving your r, small r. And then you'll have this, the same thing here. It's square. Okay. So you understand, this is, I should get, the physics demands that this should be the equation of motion. Sorry, this should be the Hamiltonian when I make this transformation. Okay. So let us do it mathematically and check whether this is the case. If physics says that, mathematically you should say get the same thing, isn't it? So how do you do mathematically? Any idea? I'll show you how to do it. What I need to do, I need to find out this operator, no, h cross s square by twice m grad r square, not r, other. That was the operator for nucleus. And this will have x, y, z component, no? Like it will be, if I write it down, it will be like twice m. Yes. Let us take one of them, say take the x1. So I need to calculate the second derivative with respect to xn. If so, then if I ask a mathematician, he will tell me, he or she will tell me that if I write this del xn, and I have gone from this nuclear coordinate to nuclear and electronic coordinate to center of mass and the relative coordinate. So if I write del x del xn, this is equivalent of saying that I take del x by del xn into del x, and this is done with when your xe is constant, plus I'll have del xc del xn when your xe is constant, not xc, sorry, x. I should be very careful. X, when your xc is constant, into del x. This is small x. Okay. So this you get from calculus. How many of you know this? This is standard calculus actually. Okay. Remember what we have done. We had coordinates like xn and xe. So I am doing in one dimension, and from there I have gone to capital X and whatever xr. We call it xr. This is what I have done. Okay. And I'm don't calling it xr again and again. What I'm going to call is small x. This is my notation. I don't want to write that x small r. Why? Because now I am interested in only the relative motion. Just go back to my previous slide. The center of mass motion, the motion of the whole body, it is not such interesting thing, translational motion. But the motion shown here, this relative coordinate, we are interested. We are very much interested. We are interested. I cannot write, some problem with writing, but this is the one actually I am very much interested in. Okay, this is the problem I'm interested in, the relative coordinates. So because of that, I'm just making this change in variables. When I do change of variables, I get this. Now tell me, what this, if this is this, then can I write down, for example, what will happen to del xe? Because I want to also calculate this, no, del xe. Can anyone tell me? Just by looking at it. It has to be what? Remember that from xn and xc, I am going to capital X and small x. Okay, so it should be what? Can anyone tell me what is the answer? Tell me in the chat box, or you switch, unmute yourself and tell me. Can you please unmute yourself? Are you guys there? So no idea about this? No one has any idea?
So the same thing, delta x by delta xe when xn is
Yeah.
constant into delta by delta x.
But xc when xn is constant, yes, delta x by delta xe when xn is constant into delta x plus delta, tell me, what will be the next one? Delta
Small x.
Small x by
Delta x. Xn constant.
Yes, sorry for this handwriting, yes. This is what you should do. And if you do this thing, maybe you should get it. So let us check what will happen to this after I do this. Your del xn. It has now become what? What is delta x by delta xn? Now remember, I write it down. What is x? Your x is m times xn plus m times xe divided by m plus m. This is my capital X, and my small x, which I was calling x of r, I'm calling it x. It is xc minus. Actually, xm. Okay. Then what is delta xn? So del xn. What is going to happen if I take a derivative of this with respect to xn? What I'm going to get? This time will be 0, but this time will give me. Tell me what is I'm going to get? I'm going to get m divided by m plus m. Yes. Plus of course you have del x plus what is del xn? Is going to be -1, isn't it? Just check, because this will give you -1, because this will be 0 and this will give you -1. So you will have something like -1 here. You have a minus, and then you have, sorry, delta del x. I'm writing very bad. Okay, this is fine. This is fine. Is this fine? Okay, then what will happen to delta del xe? Somebody tells me. Hey, someone unmute and tell me. I want to know that you guys are following. Please unmount.
Small m
Small m divided by a plus m.
m plus m into del by del x.
Yeah, it is small m del x del x. And then what is the next one?
Plus 1 into del by del x.
Del by del x. Okay. And now I have to do the algebra. These are the things I have. I have to do the algebra and put it here. So I just take only the x and n, and then I also have the other thing which I had, which I did not write, which I had was which was it? Now I'm not going to do it because this is you can do it. Maybe I'll do it this one because the next one I'm not going to do it now. So just let us do one term. So the first term is going to be h cos square by twice m into the square of this, isn't it? So I'll have kind of square of this, isn't it? And if you, and then also here also I have to make a square because of this. If I make a square of this one also give me m plus m to del x plus del x. Now I can ensure that there will be cross terms coming from here and here, and they'll come with different sign. Just check here, because one thing you can see, this is a plus b whole square kind of thing, isn't it? What I'm doing here. And this one has a plus, so the cost term will have plus. This one has a minus, the cost term will be minus. And here you have capital M here, capital M here, so it will cancel, kind of cancel somewhere. Small m here, small m will cancel. The cost terms will cancel when you add this two. We are essentially going to do, I'm going to add this two, isn't it? I'm doing only in the x direction. Add this two, and the cost terms will cancel. You can go and check. This is just algebra. Cost terms will cancel, but then you're left with the terms which are not cross terms. So this will give you something like, from here you'll get h cos square by twice m into m square divided by m plus m whole square. Okay. Plus I have done one thing. You should have told me actually. This should be small x, isn't it? You guys are not following because you are not telling me if I am doing anything, any mistake. You are not telling me. This one is like this. I'll have this. The cost I'm not writing. On the other hand, from the other term, what I'm going to get? I'm going to get Okay, is this fine? Tell me if you have any problem. Is this fine? Okay. And then if I further simplify it, what I'm going to get, first term will give me what? Can anyone tell me what I'm going to get in the first term? You can see that your m square and m will cancel. Okay, m square and m will cancel. Okay, and here also you'll have cancellations. And when you do the math, I'm not going to do it here. You'll see that you're going to get exactly this, because you're going to take this and this guy. So let me tell you, because you're going to combine, you need to take this guy and this guy together, isn't it? And this one along with this one and this one together. From here you can see that if I take this and this, I already have, if I combine these two, what I already have is, you can see this h cross square by 2 I can take common. I have something like, the problem with this, I'll have something like, okay, I'll go to the next slide. Just go to the next slide. So if I combine these two, you'll see that I'll have something like minus h cross square by 2, and then I'll have 1 over m plus 1 over small m, and then I'll have something like this. Just go back. Are you following? Because this part and this part, h cross square by 2 is 2, I can take common, then I'll have 1 over m plus 1 over small m. And what is this 1 over m plus 1 over small m? Any idea? Please unmute yourself and write.
Reduce mass.
This is 1 over mu. Okay. And I have other thing. I have this one. I have this one. This guy plus this guy. So this m, and you have m square. Okay. This will give me capital M here. This will give me small m here. And then if I add them, what I'm going to get, m plus m divided by m plus m whole square. Can you see that? What I'm going to get is, what I'm going to get here is, you have m square divided by m plus m whole square, but you had m here, plus m square divided by m into m plus m, isn't it? Whole square. The whole thing was multiplied with minus h cross square by 2, and then we had this. And if I do this manipulation, what I'm going to get? I'm going to get this thing will cancel, this thing will cancel. What I'm going to get? Can anyone tell me? 2 m plus m divided by m plus small m whole square. And this will give me what?
1 over total mass.
And this is exactly what we promised. What our physical intuition said, isn't it? This is exactly what we promised, and this is exactly what we are getting, isn't it? Are you following so far? Okay. And now what I'm going to do, that my total wave function, now I'm saying, what about the total wave function? or any, don't need to write total, but wave function itself, which is a function of your center of mass coordinate and the relative coordinate. I am writing it as a product of your center of mass product of a function which is a function for the center of mass only, which is r, times another wave function which is a of the relative coordinate. Again, I am doing what is known as separation of variables. Okay, so I'm going to do separation of variables. So when I do the separation of variable, I'll have two Schrodinger equations. One would be the one involving center of mass motion. Okay. And this will give me something like, so this one we are not really interested in. Okay. So much interested in this. This pen is giving trouble today. And but then I'll have another equation which I am very much interested in, and that is the equation you want to solve now after doing so much of work. What is that equation? Can anyone tell me? This is equation 1, but that's equation 2, and that is what you are really interested in. That is the equation for the relative coordinate. Okay. And this energy. Okay. This is the equation we are very much interested in, where we want to solve this. How many of you are convinced? But maybe I'll have a few more minutes today. But if I write down explicitly what is this, there in the Hamiltonian, I have done some mistake here. What is the mistake? Can anyone tell me? What is the mistake I have done? Tell me.
Potential energy we have not taken.
Yes, just I forgot to put. So actually you have a potential energy flux, which is your E square by 4 pi epsilon 0 to R. The whole thing operating on psi of R. But see, this one cannot be solved in this form. Even with separation of variable technique, even one cannot use separation of variable. Okay, why? Because the reason is as follows, because your R 1 over R is 1 over. So your Hamiltonian you cannot separate into X part plus Y part plus Z part. You understand? This can be done only when you have cubic or rectangular kind of symmetry. But in this case, you don't have this. What kind of symmetry you have in this problem is called spherical symmetry. So the spherical symmetry means your potential does not depend on any angle. It depends on only one only one radial coordinate. Your r is like it is a radial coordinate. So if I go away from the nucleus radially to any direction, my potential will change in the same manner. So it is essentially you have the nucleus here, and the electron could be anywhere from the nucleus. The interaction between the electron and the nucleus depend only on the distance between these two, this radial distance. So essentially, you have a spherical symmetry. The problem is spherical symmetry. And if you have spherical symmetry, you cannot use in the Cartesian coordinate system. You cannot use the separation of variable technique. What you need to do, you need to go to a spherical polar coordinate and solve it. You have to go to the spherical. And there you will see that, okay, if when I go to spherical polar coordinate, actually when I write down this equation, the same equation, equation 2, what I've written here, in the spherical polar coordinate, then I can adopt this separation of variable technique there and I can solve it. So in that case, what I'm going to do, which I'm going to do in the next class, I go from this x, y, z, these are the relative coordinates, which I could have called x r, y r, z r. I'm calling it x, y, z. I'm no longer calling it, putting the small r there. So from here to a coordinate which is given by three variables, which is r, the radial coordinate, and two angular variables theta and phi. And this is in spherical. This is called spherical polar coordinate. And in that spherical polar coordinate, actually you can solve this problem adopting the technique of separation of variables, which we will do in the next class. So in the next class we'll start from spherical polar coordinate. Okay. So thank you very much for today, and we'll wrap it up. Now I'm going to stop recording, and if you have questions, please ask me question. I'll be happy to answer your question.